that you have independent modes, and that the magnetization does a sort of a random walk through the lattice. And we know if we ask for the probability that the particle returns to the same point in time, if it does a random walk, is actually given by 1 over time to the power d over 2, where d is the dimension of the system. Yeah? So in particular, in one dimension, if the particle or the magnetization here does indeed perform such a random walk, we expect that the return probability goes like 1 over square root of t. However, this is certainly questionable to apply this theory, which was actually developed for three-dimensional ferromagnets, to a strongly correlated one-dimensional system. Certainly the excitations, we don't expect them to be independent Gaussian modes. And the other problem we have here certainly is also integrability. The XXZ chain is integrable, so we know actually that the spin transport is ballistic, whereas following such a phenomenological theory, one would actually also expect that the current correlation function, so this is the spin current operator, that this would also decay completely. Okay, so then experimentally, there are a number of systems which are sort of very good, or materials which are very good realizations of the spin 1/2 Heisenberg chain, and there have been a number of experiments done with such systems. And we can, for example, look at nuclear magnetic resonance. So if one calculates the spin lattice relaxation rate, then it's actually given by an integral over wave vector. Then we have here the hyperfine coupling constant. If we assume that this is just a constant, then we just have to integrate over momentum or wave vector, and this here is the longitudinal spin structure factor. And if the correlation function indeed follows such a 1 over square root of t behavior, then by simple power counting, we see that the spin lattice relaxation rate actually should behave as 1 over square root of the resonance frequency. And indeed, this has been observed in a number of experiments. I show you just one here. So this is spin lattice relaxation rate measured for this strontium copper oxide compound that was in Takashi Imai's group in 2001. And what's plotted here is sort of 1 over T1 multiplied by temperature T as a function of 1 over square root of the magnetic field. So this is essentially the resonance frequency. And you can see that you get sort of a linear behavior here. So indeed, 1 over T1T scales like 1 over square root of the resonance frequency. Exactly what one would expect if this diffusive theory here would be valid. On the other hand, previous sort of numerical studies have been, of the theoretical models, have been inconclusive. One should stress there is no exact solution, although the XXZ model is integrable. This problem has not been solved exactly. So mainly these results here are numerics, either exact diagonalizations or sort of short-term expansions. And both for the quantum model as well as for the classical Heisenberg model, they are kind of inconclusive if sort of spin diffusion is present or not. So then let me come to the outline. So that was a sort of motivation. Let me come to the outline of my talk. So I first want to address the non-interacting case and show you where the dominant contributions to the long-term asymptotics of the autocorrelation actually come from, and why we need nonlinear Luttinger liquid theory, which we then will apply to the interacting case. This will give us sort of a simple or simplest form for this autocorrelation function, and then I will show you that we have to sort of improve a little bit on that. There are actually irrelevant operators which lead to temperature-dependent corrections, which are actually important if one really wants to compare with numerical data. And I will also discuss here the consequences of integrability or integrability breaking. And as a last step, I will take sort of this nonlinear Luttinger theory, which I've developed before, and compare it with time-dependent density matrix renormalization group data. Yeah? So this is a numerical method which allows to obtain these autocorrelation functions up to times bandwidth times time of order 40 or 50, so relatively long times, and we can compare our theory directly with these unbiased numerical data. Okay, let me start with the non-interacting case. So we all know that by the Jordan-Wigner transformation, we can map the XXD chain onto a spinless fermion model. The X and Y part becomes this hopping part here, and the ZZ part turns into this nearest neighbor density-density interaction. If we then consider in particular the case delta equals 0, then we have free fermions, so G0 means the correlation function for free fermions, and I concentrate here to make it simpler onto the autocorrelation function, so distance 0, so all the operators sit at the same side, and then the ZZ autocorrelation function expressed in terms of these fermions turns into a particle propagator and a whole propagator here, and this can be written in the following form, so as an integral over wave vector. This integral is oscillating. It's oscillating with the dispersion relation, so epsilon of k, in this case here is minus cosine of k. And of course in the denominator here, or this factor 1 over 1 plus e to the beta epsilon k, this is just the Fermi factor which we have here. And now, of course, we can do this integral here numerically. We can also calculate it, say, at 0 or infinite temperature, where this just gives some special function, Bessel function, Struve function, and so on. But that doesn't really help us if we want to address the interacting case. So what we want to do instead is we want to asymptotically evaluate this integral and understand where the dominant contributions for the behavior at long time come from. And the important point here is that this oscillating integral here will actually be dominated by saddle points, so by points where the derivative of this dispersion with respect to k is 0, and for the autocorrelation function, this happens at k equals 0, so at the lower edge of the band, and at k equal pi, which is the upper edge of the band. Yeah, so important is that the long-time asymptotics is actually not dominated by the Fermi points, which are the points which are usually kept in Luttinger liquid theory, where the low energy excitations happen, but rather by this lower band edge and the upper band edge. And this is even true at 0 temperature. Yeah, and that's the reason why regular Luttinger liquid theory cannot describe the long-time behavior inside the light cone, and we also have to keep track of what is happening at the lower and the upper band edge. And the way to do that brings me back to the talk you heard last week by Rodrigo Pereira. It's the same idea. So we take the fermionic operator and we actually use a mode expansion where we keep 4 different kind of contributions. The first 2 is what you usually do in Luttinger liquid theory. You linearize your dispersion around the 2 Fermi points, and this gives you left movers and right movers. But in addition to that, we also keep a low energy hole here, which is given by this d bar operator, and a high energy particle, which sits here at the upper band edge. So this is the idea. So at temperatures much smaller than the bandwidth, we keep states near the Fermi points, which are a bit smeared because of the finite temperature, and also near the saddle points. And the important approximation we make here, which is sort of justified at very low temperatures, is that there are only exponentially small temperature corrections for these impurity modes, so for these modes which sit at the band edges, and that we can ignore these corrections. Yeah, so basically these modes here, they don't feel the temperature, whereas these modes here, they do, because they sit right at the Fermi edge. Okay, then the low energy modes, of course, this is well known. They have a linear dispersion. So if we want to understand the propagator at low temperatures, we can just use the conformal feed theory result. So for the right and for the left movers, the propagator is just proportional to temperature divided by this hyperbolic sine function of temperature times time. And on the other hand, for the band edges, so from here on I will set the bandwidth equal to 1, so this exchange coupling J is equal to 1. Then we have a parabolic dispersion both for the hole and for the particle, and that means that these impurity propagator will actually decay very slowly, like 1 over square root of t. Yeah, and this slow decay is the reason why actually these impurity modes dominate the long time behavior. And now the idea is basically, if we go back here, so this is our correlation function for free fermions. We have a particle and a whole propagator, and each one of them can now either be a low energy propagator, so a psi r, psi l, or it can be a high energy particle or a hole. So we just have to put in these different combinations, and if we do that and keep all the prefactors, we get these 3 terms here. The first term here actually comes from having a high energy particle times a whole propagator, so if both of them here are, so this is high energy particle and the other one is the whole, then this gives us this contribution here, which oscillates with 2 times j, so j is z equal to 1, and decays like 1 over t, because we get 2 factors of 1 over square root of t. The next term is the combination of either a high energy particle with right or left movers, or a low energy hole with right or left movers. So you have 1 times this propagator times this one here, so you get a 1 over square root of t, and then you also get this Sinch factor here coming from the low energy mode. And last but not least, this contribution is the one we're used to from Luttinger liquid theory. This is the contribution if both hole and particle propagator are given by low energy modes. Yeah, and the important point to notice here is that if temperature is larger than 1 over t, then this term here is actually exponentially small. So if t times, so time times temperature becomes large, then this is exponentially small, this one as well, and everything gets actually dominated by this first term here, which is the term which comes from a high energy particle times the whole propagator. And now we can actually check if this is a good approximation for our integral, so for the exact solution. So let me go back, and okay, so equation 7 is this one here. This is the approximation by using this theory here. On the other hand, of course, we can just do this integral here exactly for all temperatures, or numerically exactly, just by evaluating this integral. And we can compare the solutions, and that's shown here. So what I plot here is the real part of the autocorrelation function. So it has real and imaginary part. I just show the real part here as a function of time. And I have 3 different results here. On the one hand, I have numerical density matrix renormalization group results. This theory doesn't, or this method doesn't know anything about free fermions. So for this method, free fermions are as hard as the interacting case. And you can see that we get results which are a nice agreement with the exact evaluation of the integral up to times of around 50, so fairly long times. And you can also see that this approximation, which is the dashed line here, agrees with the exact result very well, except for very small times. Yeah, so it's an excellent approximation. And the last thing I want to show you is if you take the real part of the autocorrelation function and you multiply it by t, you indeed get something which oscillates and does not decay. Yeah, so which indeed shows the dominant contribution goes like 1 over t. Okay, so this is the non-interacting case. Now let's go ahead and apply the same idea to the interacting case. And here the starting point is an effective low energy theory in the following way. So this is the Hamiltonian density, and it consists of the low energy part. So these are, as the usual, sort of bosonic phi field. This is the dual field theta. V is the velocity. This is the part we're used to. But now we also have to keep the high energy particle and the low energy hole. And these are these 2 parts here. Yeah? So both of them have a parabolic dispersion. So these are these parts here. This is the right and left movers. And these are actually coupled with a coupling constant alpha. So this coupling constant alpha actually couples sort of the density of low energy modes to the density of particles and holes. And then there is also a direct interaction V between the high energy particle and the hole. Yeah, so this is sort of the low energy theory we want to start from. And the advantage actually of applying this to an integrable model is that a number of parameters can be fixed, and this will give us a theory which we can compare much more easily with numerical results. Yeah? So often if you do field theory, one of the problems is you have many sort of unknown amplitudes, and then if you try to fit something, it's not very convincing. Here, if you do it for an integrable model, many of these parameters which will show up are actually known exactly by comparing with a beta-ansatz solution for other quantities. In particular, we know what the velocity and the bandwidth epsilon is, which is also equal to 1 over m here, and just given by this well-known expression. The Luttinger liquid parameter is known, and this is also related to this dimensionless coupling constant between the low energy modes and the high energy particle. Again, is given by this expression here. And the impurity interaction, so interaction between particle and hole, we know for small delta. So we don't know it exactly, but we can sort of bosonize the model. And for small delta, in an expansion in delta, we find that V is given by minus 4 delta plus higher order corrections in delta. And this theory here was first motivated and used by the group by Leonid Glassman. And what they then showed is that these modes can actually be decoupled. So the term which sort of stops us from solving the model is this interaction here between low energy modes and high energy particles. And one can actually apply a unitary transformation which attaches these strings here to the particle and hole, and which leads to a decoupling. And then one can actually calculate things in this theory. Okay, then let's see what we get in simplest approximation for the autocorrelation function. So one first important point to note is that this impurity contribution actually changes abruptly for finite interactions. So once you have you go to finite delta, then you have this V term here, so which is this direct interaction between particle and hole, and this actually modifies this particle-hole contribution in the propagator dramatically. So instead of decaying like 1 over t, it actually changes to 1 over t squared. Yeah, and this can be sort of calculated exactly. So there's basically a delta function interaction between particle and hole, and one can sum up sort of the ladder diagrams, and this gives this dramatic change from 1 over t to 1 over t squared. Next, we can look at the impurity boson contribution. This is just a straightforward generalization of the result I've shown you for the non-interacting case. So this here, this 1 over square root of t still comes from the high energy part, so from the high energy propagator. And then the low energy part is now just taken to the power of eta, where in the simplest approximation, eta is just the Luttinger parameter k. And this oscillation here, so this oscillates with half of the bandwidth, and this bandwidth epsilon here is in lowest approximation also still just the bare bandwidth of, it's related to the velocity here, yeah, so it's given by the velocity here. Okay, and then we have the Luttinger liquid contribution, so the low energy contributions, and this is the sort of, if you do it for finite distance, the non-oscillating part, this is the oscillating part. They are also both well known. And in particular, we also even know these amplitudes here, A prime and B prime. They have been calculated by Lukyanov and co-workers. So, and in this form, this is actually a rather straightforward generalization of the zero temperature result, which has first been derived by Rodrigo, Steve White, and Ian Affleck in 2008. But actually, it turns out that this sort of too simple to give you good agreement with numerical results. There is actually a significant renormalization of parameters in this theory, and this renormalization comes from irrelevant operators. So here in this theory, we haven't included, I mean, these are all sort of dimension 2 operators, so we haven't included anything of higher dimension. And so the next step would be to write down all the kinematically allowed terms of dimension 3. And these are these 1, 2, 3, 4 terms which I've written down here. So they all involve some interaction between the low energy and the high energy modes. And again, by using bosonization, we can actually calculate what these coupling constants are here. So we find in particular that this coupling constant G here is proportional to minus delta, this mu minus to minus delta over square root of pi. And then we find, at least to lowest order in delta, that G prime and mu plus are actually 0. And taking these operators into account, we actually find a renormalization of parameters in the autocorrelation function. So we find an effective decrease of the bandwidth. So the bandwidth now becomes temperature dependent and scales like the sort of bare bandwidth plus C times G times T squared. So it decreases as a power of T squared. So keep in mind G is negative, so this is a decrease of the bandwidth. And on the other hand, we find that this contribution here, which comes from the low energy part times high energy particle, starts to decay slower, so this eta parameter actually also gets renormalized and it gets reduced so that we get a slower decay. Yeah, so I'm talking about these contributions here. So this epsilon gets renormalized, so that means the frequency at which this contribution here oscillates changes, and also this exponent here is renormalized, so it gets reduced, so that these oscillations actually decay slower than would be expected in this simplest approximation here. And the important point here is that this temperature dependence we find, this T squared here, and T, this actually will hold for arbitrary anisotropy delta as long as the temperature is small compared to the bandwidth. The prefactor here, of course, we can only calculate in lowest order in delta. Yeah? So this will change, but the temperature dependence should be fixed. And the way we've done that is the following. So the most important part of these dimension 3 operators is this term here, where you have right-moving density squared coupled to the density of the whole or the particle with coupling constant G, and that gives rise to two types of Feynman diagrams. On the one hand, we have the impurity propagator here, and this impurity propagator gets a self-energy, and the self-energy is just the expectation value of this del x phi right or del x phi left squared. And if you expand that and extract the cutoff independent part, you find indeed that this self-energy goes like G times T squared, and the self-energy just enters here into the impurity propagator, so it just gives you a renormalization of the bandwidth. Yeah, so that was what I was talking about before. And the other thing is we have also a vertex correction, so these solid lines here are again the impurity propagators, the dashed line is the low energy mode, and there will be vertex corrections, which are these sort of little bubbles here you get, and these polarization bubbles, they can also be calculated, and they will give you this renormalization of this exponent eta here. Okay, so this is sort of, I'll show you in a minute, sort of a comparison of this theory then also with numerical data, but before doing that, let me just take a step back and discuss the difference between an integrable system, so like this XXZ model I have discussed so far, and a system where integrability is broken. Yeah, so the important point here is that integrable systems have a complete set of local conserved charges. Yeah, so you have a set of conserved charges, which I denoted by Qn, and these charges, they commute with the Hamilton operator H. And what does that mean now for the field theory? Well, for the field theory, that actually means that there is some fine-tuning going on. So in order to have these charges here conserved, not all the terms which for a general model would be kinematically allowed are actually there. So some of them are forbidden by the conservation laws. And I'll just show you one example here, which is very important in this context. So luckily, the first non-trivial conserved charge, so Q2 is the Hamilton operator, Q3 is actually the energy current for the Heisenberg model. And we can define the energy current density just by the continuity equation. So this is just lattice form one dimension of the divergence, so divergence of J is equal to minus the time derivative of the density, and this, of course, we can write as a commutator of the energy density, which is this script h here with the total Hamiltonian. And if the energy operator is conserved, then of course that means that if we integrate the energy current density defined in this way, that this integral has to commute with the full Hamiltonian. Now if we go back, there was one term in the theory which is kinematically allowed, which has this form here, so this G prime, then this here low energy part and this high energy part here. And what we can show actually is, I don't want to show you the calculation, I just mention it here, that the conservation of the energy current actually implies that this G prime is 0 to all orders. Yeah, so if G prime is non-zero, then actually this energy operator, if you bosonize it, it would not be conserved. Yeah, and this is very important because this G prime interaction has been looked at before by Castronetto, Fischer, Glassman, and others. And this is actually exactly the term which introduces a non-zero impurity decay rate for finite temperatures. Yeah, so integrability actually forbids here in this case that this term is present, and this gives us an important difference between an integrable and a non-integrable system. So this is the impurity whole contribution, so where we have high energy particle propagator times low energy whole propagator. And for the integrable model, we have some amplitude b of t divided by t squared, and then this oscillating factor with the full bandwidth. Now, if we break integrability, then this will actually get a finite decay rate, so there will be an exponential decay, and this decay rate here will be proportional to G prime squared times temperature squared. Yeah, so this part of the autocorrelation function indeed does know about the integrability of the system. Okay, and then there is, so far, if we go back to the result here, just go here. If you remember my introduction, so the question was, is there diffusion or not? And if you look at this result here, clearly there is no diffusion. We have a term which decays like 1 over t squared, and we have two terms which are exponentially decaying at long times. So what's going on? Is there something we're missing here, or is there something sort of wrong with these experiments which do see this diffusive behavior? And indeed, there is something we have been missing so far, and this is actually Umklapp scattering, which in the XXZ model is also an irrelevant operator, but actually for the dynamics, it has a sort of a profound effect, and one is not allowed to ignore it. So Umklapp scattering is given by this cosine term here. K is again the Luttinger parameter, lambda is the amplitude of Umklapp scattering. And we can calculate the boson propagator, so the propagator for the low energy modes, in a self-energy approximation, taking this Umklapp scattering into account, and then this Umklapp scattering actually leads to a finite decay rate in the boson propagator, and this decay rate in second-order perturbation theory, of course, scales like lambda squared, and it goes like temperature to the power 8 times Luttinger parameter k minus 3. Yeah, so that's very important. And now if we know this boson propagator, we can actually calculate the Green's function at finite distance r and time t by performing this integral. So we have to take the imaginary part of this retarded function. This is the sort of usual sort of factor going from the retarded to the sort of normal function, and we have this frequency and momentum integral. And the important point is, without the self-energy here, this integral only has poles. And if you evaluate the contributions from these poles, you get back the usual Luttinger liquid result. But now, because of this additional self-energy here, we also get branch cuts. And this completely changes the long-time dynamics of this correlation function. And we can actually solve these or extract these contributions analytically in the limit of very long times, so where time is much longer than 1 over the decay rate, and this decay rate here much larger than 1 over t. And in that case, we indeed find a contribution which is diffusive, which comes from this branch cut here, and which goes like 1 over square root of t, and we can even extract the amplitude exactly. And everything which I've written down here is known exactly for the XXE model, so we get a contribution where all parameters are actually known. Yeah, so, and more generally, so this was for the autocorrelation. If you go back and look at the correlation function for finite distances, we indeed find this diffusive form, which was sort of predicted by the phenomenological theory, although in a much more restricted range. So here, this diffusive contribution only dominates in this regime here, where sort of distance between these two operators is much smaller than 1 over the relaxation rate, and this is much smaller than time. So we have to be really deep inside the light cone. Only then do we get this diffusive contribution here. Okay, so this brings me to the final result for the autocorrelation function. So we have this diffusive contribution here, which is actually the dominating term, so it goes like 1 over square root of t. Then we have the 1 over t squared contribution, which comes from a high energy particle and low energy hole. We have this cross term here, where a high energy particle or low energy hole interacts with the low energy modes at the right or left Fermi point, and this is an exponentially decaying contribution in times. At long times, this will exponentially decay. And then we have these two contributions here, which are well known, which are the regular Luttinger liquid contributions. Okay, and here in the integrable case, we actually get a sort of very powerful theory, because lots of these parameters are known exactly. We know this prefactor gamma of the diffusive decay. We know A prime and B prime, thanks to the work by Lukyanov and others. We do know that at 0 temperature, this eta here is just a Luttinger parameter, and the bandwidth with which this oscillates here is just given by the velocity. And this phase shift here, phi, is also known exactly at 0 temperature. And we can calculate the finite temperature corrections to first order in delta. So basically, the only parameters here, which we don't know at all, are these two amplitudes here. So the amplitude A of t of this cross term, and this amplitude B of t of high energy particle and hole. So now we can take this theory and actually compare it to numerical results. And this is shown here. So as an example, I choose the XXZ chain with anisotropy delta equal 0.3. And what I plot here is always the square root of time times the autocorrelation function. And the autocorrelation function has a real and an imaginary part. So these red curves here are always the real part, and the blue curves here are the imaginary part. The correlation functions are plotted as a function of time. Maximum time we reach here in the simulation goes out to 45 in units of the inverse bandwidth. And I show you two temperatures here. So the first two here are for temperature 0.07, and the one below here for temperature 0.25. And the symbols, so these little stars, are the DMRG results, and the solid line is a fit with this theory here, where essentially B of t and A of t are the only fitting parameters. And you can see this gives quite a nice agreement, so you get a nice fit of the numerical data. In particular, you can extract what this prefactor here is of the diffusion. So if we leave that as a free fitting parameter, then for temperature 0.07, we find that this is rather small, so you cannot really extract it from the numerics. So this is the 0 line, and it looks like almost it oscillates around 0. And indeed, from theory, we get this diffusion parameter here, which is of the order 10 to the minus 5. So this is basically below what we can do numerically, at least for the simulation times we have at hand here. It looks a little better for larger temperatures, temperature equal 1/4. So keep in mind this relaxation rate gets larger and larger with temperature, so it scales like here's a t, and then it gets multiplied by square root, so by this factor here. So if we increase temperature, then also gamma gets larger. Of course, we shouldn't go to too large temperatures because then our low energy theory breaks down, so it's a little bit of a subtle thing to find temperatures where one can compare easily, but temperature 1/4 works quite well. So here you can clearly see this oscillates around something here at long times, which is not zero. So these oscillations, they stay above the zero line here. And from a fit, we find this gamma of the order 6 times 10 to the minus 4, and the theory predicts it to be 8 times 10 to the minus 4. So we would say this is in quite reasonable agreement. And just to show you one other example, so same kind of figures now at anisotropy 0.8, again 2 temperatures. In this case, temperature 1/6 and 1/4. Again, you can see here at this lower temperature, it oscillates and the oscillations die out and it goes to something which seems to be above the zero line for the real part here, and you can see it even more clearly for temperature 1/4, where this here indeed goes to some constant which is non-zero, which confirms that we have a decay like 1/1 square root of t. And if we fit, then again we find quite reasonable agreement. So the fit here in the first case gives 3 times 10 to the minus 4. Here we get something like 5 point something, 10 to the minus 4. And again, in this case here, it's also in good agreement with what we calculate analytically. Okay, then also we did get these results for the renormalization of the effective bandwidth and also for this exponent of this oscillating decay eta here. And the prediction was that the effective bandwidth decreases with t squared, whereas this exponent here goes down linearly in t, and this is indeed what we find. So from the fits we can extract this oscillation frequency, and the extracted data are these points here, and we can nicely fit them by a quadratic fit. So this is this dashed line here, and this dashed line is in reasonable agreement in this case with this solid line, which is actually the lowest order result in anisotropy delta. Yeah, so this works reasonably well. For the exponent, again, we expect sort of linear scaling in temperature. These are the data we extracted from the fits, and again, they indeed follow such a linear behavior. But in this case, actually, our lowest order in delta theory gives something, a prefactor, which is much too small. And actually, that's not surprising, so I think we kind of understand why that's the case, but we cannot really improve it because we can only calculate these factors here in lowest order in delta, and delta equal 0.3 is probably already kind of large for this sort of low energy, for this low delta expansion. Okay, and last but not least, I told you that this diffusive contribution actually comes from Umklapp scattering, so from this term here. On the other hand, we know that Umklapp scattering should only be important for zero field. Once we introduce a finite field, we can actually gauge away the field, and this will make this Umklapp scattering term oscillating. Yeah, and once these sort of wavelengths of these oscillations, when they become sort of large compared to 1/temperature, so to the correlation length, then we should actually drop this Umklapp scattering term, and we would expect that this diffusive term, therefore, at large fields doesn't play any role, so that it disappears. And that also seems to be confirmed by the numerical results. So here I show you data for anisotropy 0.8 again, temperature 1/4, relatively large field, which corresponds to a magnetization of 0.3. And if we plot now square root of time times this real part of the connected correlation function, so here I subtracted the disconnected part, so minus m squared, then indeed we get something which seems to decay faster than 1 over square root of t. Yeah? So this also seems to be consistent with this result. Okay, then let me come to the conclusions. So the aim was to develop a finite temperature nonlinear Luttinger liquid theory. More specifically, I investigated the long-time asymptotics of this longitudinal spin-spin correlation function in the XXZ chain. The main idea, take-home message here is if one wants to do that, one needs a mode expansion, which includes not only the Fermi points, but also the band edges. These have sort of quadratic dispersion and therefore propagators which decay very slowly as 1 over square root of t. If one wants to go to finite temperature, then for the linear modes, one can just use the CFT results. And the approximation here which we used is that the edge modes are not affected by temperature, so the corrections are exponentially small in temperature, so they go, I mean, you have a Fermi factor in there which goes like e to the minus j over t. But of course, once temperature becomes comparable to the bandwidth, this will break down and we will no longer have a separation of energy scales. Yeah? So this is really a theory which only works at temperatures which are small compared to the bandwidth. So this gives you sort of the simplest theory one can think of. If one wants to improve on that, then one can take also dimension-free operators into account, and this is actually important to get this nice agreement I showed you with the numerics. And in particular, they give us a renormalization of the bandwidth, so this gets renormalized like t squared, and this oscillating decay also becomes slower and gets reduced linearly in temperature. The surprising thing is that even in this strongly correlated system, at the end of the day, in a limited sort of regime, so it's much more limited than what you would expect from the phenomenological theory, but nevertheless, there is a regime where you indeed find diffusive behavior in this spin 1/2 XXZ chain, and these predictions which we got based on this theory, they seem to be nicely confirmed by this density matrix renormalization calculation, which I showed you at the end. Yeah, so our main claim here would be that the XXZ chain in this regime here, so small magnetic field, which is small compared to temperature, small compared to bandwidth, we indeed have spin diffusion in the sense of a 1 over square root of t long time decay of the 2-point correlation function. And this indeed then gives us some very strange behavior in this integrable model where actually ballistic spin transport, so the spin current does not decay, actually coexists with diffusion in this spin-spin correlation function. And this, we believe that this diffusion is generic, so even if you break integrability, this 1 over square root of t in the spin-spin correlation function will stay, whereas ballistic transport is not, so this is really directly related to the non-trivial sort of conserved charges you have due to integrability. Okay, and this approach, I mean, I showed you that for the XXZ chain, but it's not restricted to that, so it can also be applied to a number of other critical models, either lattice models or also models in the continuum. And yeah, that's all I have to say, so thank you for your attention.